We are interested in solving second order linear non-homogeneous ODEs. In the previous lecture, we have learned that in order to get the general solution of second order non-homogeneous linear ODEs, we should get the general solution of the associated homogeneous ODEs and one particular solution of the non-homogeneous ODE. The general solution of the non-homogeneous ODE is given by the sum of the general solution of the associated homogeneous ODE and a particular solution of the non-homogeneous ODE. In this lecture, we will learn two methods of finding a particular solution of the non-homogeneous ODE. One of the method is method of variation of parameters and the other method is method of undetermined coefficients. First, we will learn the method of variation of parameters. Suppose yx is equal to c1y1x plus c2y2x is the solution of the associated homogeneous ODE of a non-homogeneous ODE. By that I mean that y1 and y2 are two linearly independent solutions of the associated homogeneous ODE. Let the homogeneous ODE be Ly is equal to y double prime plus px y prime plus qxy is equal to 0. In order to find a particular solution of the non-homogeneous ODE, we replace the constant C1 and C2 in the general solution of the homogeneous ODE by functions V1 and V2. That is, we vary the parameters C1 and C2 by replacing them by functions. So we consider a particular solution ypx is equal to v1x y1x plus v2x y2x of the non-homogeneous ODE. If it has to be a particular solution of the non-homogeneous ODE, namely Ly is equal to Rx, then when you replace y by yp, that is when we write here yp double prime plus px yp prime plus qx yp, it should be equal to Rx.
So the derivative of yp will be v1 y1 prime plus v2 y2 prime plus v1 prime y1 plus v2 prime y2. We assume another condition on this, namely v1 prime y1 plus v2 prime y2 is equal to 0. So the later two terms is 0. So derivative of yp will be equal to the first two terms, that is yp prime is equal to v1 y1 prime plus v2 y2 prime, and so that is the double derivative of yp will have four terms, that is yp double prime is equal to v1 y1 double prime plus v1 prime y1 prime plus v2 y2 double prime plus v2 prime y2 prime. We substitute yp double prime and yp prime in this equation, as well as we substitute y is equal to v1 y1 plus v2 y2. So here there are two terms, here there are two terms, and here there are four terms. So total there will be 8 terms on the left hand side and 1 on the right hand side. So on substituting we get this, there are 8 terms on the left hand side and 1 on the right hand side. So clear that in this equation we are substituted for y double prime, y prime and y using this equation, and this equation to get this equation. Now we observe here that y1 is a solution of the homogeneous ODE and y2 is a solution of the homogeneous ODE. So both these terms are 0. Therefore, the only thing that survives here is these two terms and the last term. That is, we have v1 prime y1 prime plus v2 prime y2 prime is equal to Rx. That is same as what is stated here. So this, along with one more equation that we have here, which involves v1 prime and v2 prime, we take them together and we solve this system of linear equations in variable v1 prime, v2 prime. So this system of linear equations can be written in the matrix form in this following way: a 2 cross 2 matrix with entries y1, y2, y1 prime, y2 prime is multiplied with the column matrix v1 prime, v2 prime, and that is equal to the column matrix 0, Rx. Now, in order to find the value of v1 prime, we know that v1 prime here is equal to the determinant of the matrix, where the first column here is replaced by 0 Rx and second remains as it is, divided by the determinant of this coefficient matrix, it is nothing but the Wronskian. So what I just stated is v1 prime is equal to the determinant of, with entries 0, y2, Rx, y2 prime, divided by the Wronskian of y1, y2. Similarly, we want to compute v2 prime, then that is equal to the determinant of the 2 cross 2 matrix, where the second column is replaced by 0 Rx and the first remains as it is, and this divided by the determinant of this matrix, which is the Wronskian. So y2 prime is equal to this matrix determinant divided by the Wronskian. So these are the derivatives. So this derivative is equal to what you obtain by multiplying 0 with y2 prime minus y2 Rx in the numerator divided by Wronskian, and this is y1 times Rx divided by the Wronskian. So in order to obtain v1, we have to integrate this. So v1 is equal to minus integration of y2 Rx divided by the Wronskian dx, and v2 is equal to integration of v1 Rx divided by Wronskian dx. Hence we have the particular solution to be equal to yp is equal to v1 y1 plus v2 y2, which is equal to, we just interchange this. So first write v2 y2 and then write v1 y1, because v1 is involving a negative sign. So it is equal to y2 times the expression that is here, that is integration of y1 Rx divided by Wronskian dx minus y1, and from here we get integration y2 Rx divided by Wronskian dx. This was the method of variation of parameters, and to get the general solution we have to add to the general solution of the associated homogeneous differential equation this particular solution that we have obtained. We'll see an example with the variation of parameters method. Consider the differential equation y double prime plus y is equal to cosec x. Step 1 is we consider the associated homogeneous equation, that is y double prime plus y is equal to 0. Now to solve this homogeneous equation, we have to look at the roots of m square plus 1. From that we get the roots to be plus minus iota, and so we get a basis of solution of the homogeneous ODE. y1x is equal to sin x and y2x is equal to cos x. So the general solution of the homogeneous ODE is c1y1 plus c2y2. Next, you are interested in calculating a particular solution of the non-homogeneous ODE using variation of parameters. So first we calculate the one scan of these two elements of the basis. So we have this y1, y2, y1 dash, y2 dash. So sin x, cos x, and derivative of sin x is cos x, derivative of cos x is minus sin x. So this gives us the one scan to be minus 1, minus sin x square minus cos x square is minus 1. So recall the v1 is equal to minus integration of y2 rx divided by one scan dx. Here we have already calculated the one scan, that is minus 1, and y2 is cos x and rx is cosec x. So we write those things here. So this is integration of cos x by sin x dx. So which is nothing but log of mod sin x. Next we calculate v2. v2 was given by integration y1 rx divided by 1 scan dx. 1 scan is minus 1, y1 is sin x, and rx was cosec x. So when we write here, we get sin x cosec x divided by minus 1 dx. So it is sin x divided by sin x with a minus sign. So it is integration of the minus 1 function. Its integration is minus x without the integration constant. So the particular solution is given by yp is equal to, so you multiply the v1 with the y1 and v2 with the y2. So y1 is sin x, with that we multiply ln mod x mod sin x, and y2 is cos x, with that we multiply v2 which is minus x. So we get yp is equal to sin x ln mod sin x minus x cos x. So what about the general solution? You can compute yourself and write down the general solution. We'll look at another example. So find the general solution of y double prime minus y prime minus 2y is equal to e raised to x. So basis of solution of the corresponding homogeneous equation is, so what do you do for that? The basis turns out to be y1 e raised to 2x plus, and y2 is equal to e raised to minus x. So for that we take the corresponding characteristic equation, namely m square minus m minus 2 equal to 0, and find its roots. Its roots are 2 and minus 1, and so the real independent solution which forms the basis of the homogeneous equation are e raised to 2x and e raised to minus x. Now we will use the method variation of parameters. So first we have to calculate the one scale here. So we write y1, y2, y1 prime, y2 prime. So y1 prime is 2 e raised to 2x clearly, and y2 prime is this minus sign in the front, minus e raised to minus x. we compute the one skin, we have to multiply this with this minus this multiplied with this minus 3 e raised to x. So v1 is equal to minus integration y to rx divided by 1 scan dx. 1 scan is minus 3 e raised to x, y2 is e raised to minus x, and rx is e raised to minus x. So together we have e raised to minus 3x divided by 3. Its integration is minus 1 by 9 e raised to minus 3x. Similarly, y2 is integration y1 rx divided by 1 square dx. Here y1 is e raised to 2x, rx is e raised to minus x divided by minus 3ex, which is the one scan. So this is integration of minus 1 by 3 dx, which is minus 1 by 3x. Both v1 and v2 we take without the integration constant. Once we know v1 and v2, we multiply v1 with y1, v2 with y2, and their sum will give us a particular solution of the non-homogeneous ODE. So we multiply this with this, we get minus 1 by 9 e raised to minus x from here, and we multiply this with this, we get minus 1 by 3 x e raised to minus x. So this is a particular solution. The general solution will be the general solution of the homogeneous ODE plus this particular solution. But we see that this is a arbitrary constant and this is a fixed constant. We can combine these two terms and we may write using some other constant C2. The general solution is C1 e raised to 2x plus C2 e raised to minus x minus 1 by 3 x e raised to minus x. Though we are using the same C2 here, the mean is this C2 is different from this C2, just that the C2 is absorbing this constant. We see one more example using variation of parameters method. Find a particular solution of y double prime plus 4y is equal to 3 cos 2t. The basis of the corresponding homogeneous equation is y1 is equal to cos 2t, y2 is equal to sin 2t. Here again we had observed the associated characteristic equation can be m square plus 4 equal to 0, found its roots, and from that we got the solution of the homogeneous differential equation. Now we want to use the method of variation of parameters, so we have to calculate the one scan. The one scan in this case comes out to be 2, and so we can compute v1 using the formula that we know from the previous slide. So for v1 we have minus y2 that comes here, then the rx, that is 3 cos 2t divided by the one square, that is 2. So this together we can use the trigonometric formula, multiply the denominator by 2 and numerator again by 2 to convert this into sin 4t. So it will be 3 by 4 sin 4t with a minus sign, and its integration will be 3 by 16 cos 4t. Similarly, v2 is integration of y1, which is cos 2t, times rx, which is 3 cos 2t, divided by the one square 2 and dt. Here again you can use the trigonometric formula.
Cos 4t plus 1 divided by 2.
You can multiply that by 3 by 2 and integrate, we'll get 3 by 16 sine 4t plus 3 by 4 t. So the particular solution here is yp is equal to v1 y1 plus v2 y2. And you can complete it by writing the v1 v2 here and y1 y2 here.